Thanks, Rick. Steve Luxian, I go by Lux. I'm the Deputy Director of Assure, and just real briefly on Assure, it's an alliance of 23 universities, including global, in Canada, Great Britain, Israel, I'll miss somebody, Spain. We also have relationships now with Israel, a civil authority, Canada Civil Authority for Aviation, and Spain. My boss right today and the head of the FAA UAS is currently in Spain doing discussions about how we can support them. So these drones can just do amazing things. My background came from military. I was a flyer in the military most of my career, but late in my career we stood up the UAS capability in the Air Force, and I watched this thing explode. We're limited only by the creativity of the minds of what we can do with them. But there are some real challenges. And well, before that, like Rick mentioned, it really comes down to the data, right? Primarily the sensors, the data, how we process it, how we can make your lives more efficient, your jobs more efficient, easier done than, or safer done than what we do currently with manned platforms. However, there are some real challenges in privacy, very crowded airspace, running into each other. So that's kind of where I'm going to approach it today. I'm going to approach this situation from the regulatory risk that you face as you try to move forward. And what Assure is trying to do is break through that risk and lower that risk so we get more and more companies out there operating. But I'd also ask you to think, as I discuss some of our projects today in more depth, of, okay, on your plant, what I'm doing with the FAA is establishing a minimum standard. When you start dealing with refineries and pipeline runs and power line runs, especially, let's get back to refineries, the safety level has to be much, much higher than what we are going to propose. So working with research and folks to help you out and us understand your problem could potentially benefit both you and us in the future in how we regulate and how we establish safety in this field. What I'll go through is where the FAA is right now. Currently, they have a research roadmap out, new administration. It's a new administrator of the FAA, and it's sitting on their desk trying to figure out, are they happy with the way we're going to proceed in research? I have not been privy to what that new research plan. So what I have is their strategic vision of where they're going, and we're working on, okay, what's the next steps 2-3 years out? We'll also then cover I'll give you a quick overview of what we have done in research, and then I'll take you a deeper dive into some of the collision studies we've done, air-to-air collision, and then what happens when a UAS hits people on the ground. One's generally a good news story. One is, and I would say, is an expected story, and it's not good news when anything in the air collides with something else in the air. Okay, strategic plan. If you look at this chart, on the horizontal axis, the x-axis, from left to right, it's a time notional. So the closest to today is on the left side, further out is on the right. Also in this chart, more rural applications, think in agriculture uses or maybe pipeline inspections in the middle of nowhere, to more urbanize those package delivery in cities and urban environments on the right. And then on the left side in the y-axis is all about altitudes, and those who know aviation, there's different categories of airspace. So where we are today is in that low altitude. You can see those bubbles called visual line of sight, VLS. The FAA is working hard with us as their university research arm, but also they have other researchers trying to deal with, okay, what is the minimum standards we need in this area to safely do those applications in the rural environment. Then they expect to be able to move up actually into their what's called Class A airspace above 18,000 feet. Under their current regulations, plus we're going to have to add some for communication systems, how to deal with things like lost link, those kind of applications. But they foresee they're going to certify airplanes just like they certify UAs, unmanned aircraft, just like they do regular aircraft for that airspace. The power equipage of those we expect to be much, much larger, so you can operate with transponders and radars and all that at that altitude. Coming back in time, now you move down in that low altitude area into more of the urban environment. This is not trivial. There's all kinds of detect and avoid situations that need to occur, traffic patterns through cities, a new crane is added. How does that affect things? Micro weather inside of cities. Anybody who's ever been a kayaker or on a river canoeing, you see all the eddies and flows. Depending on the winds through a city, that can change at any one moment and have an effect on how the two UAS cross each other. Or a big crosswind, you're going down a little street and you hit Broadway and it just blows you, well into down the street and you can't get back around the corner, or you could have a conflict with other aircraft. So we're doing a lot of work in that area, but that's coming more in the future. And then just a situation of all the airspace where we enable UA to integrate in a non-segregated, non-cooperative, some situations, so that these UAs can detect and avoid one another and move throughout that airspace. Now, to do that, each one of these things and where we are today is looking at operations over people, expanded operations, which mean beyond visual line of sight. So if you want to do anything like an oil line inspection, power line inspection, those kind of things. And there's a lot of pressure on the FAA and our commercial folks to do small UAS. But that comes that we have to define, do the research and safely define things like how to ID a specific UAV. We were close to flight over people, but then Department of Homeland Security and the FBI said, now wait a minute, how do we know over a sporting event if that's a friendly UA or a bad one? And we couldn't answer that question initially. So we've taken a step back to do detection, flight pointing systems. That's that low altitude authorization and notification called LANCE. Beyond visual line of sight and detect and avoid, we're going to see some projects that we have in that area trying to actually define what that's going to be to enable anything beyond your visual line of sight, which is a lot of applications in the commercial space. There's command and control performance. We want you to be able to not lose link to your aircraft. If you do, to be able to regain it, but then we don't want a cyber attack to get into that system and easily be able to take over your UA. So there's a lot of work starting in that area and how to deal with it. So just a quick look at what we've done. Where we have been, primarily you can see up top is we did some initial certifications, but with Part 107 for the smalls it became not so important. But we started looking into the detect and avoid program. They've surveyed the whole industry, tried to find out what were the needs, and the next phase, what I'll brief here in a second on another slide, is we're going to start doing testing to figure out what the minimum standards will be, what are the requirements for you to be able to go out and fly a UAS beyond visual line of sight. The two studies that I'm going to cover in detail, so I'll skip through now, are the collision severity studies. People are very, very concerned, rightfully so, of what happens when a UAV, is flying around and hits over top of people in a crowd, when it hits somebody in a crowd. What happens when it hits my airplane that's coming in to land? We've done work there. Maintenance, modification, and training. We've done a lot of work there. An airliner like a 747 has an intensive requirements in that area. Obviously, you don't need that for your 2-pound DJI Phantom 3. But what do you need? What are the requirements? How do we scale that for the different sizes in between? A lot of work also on human factors, the design of the ground control station. It's the cockpit of the future. Is there things we need to change? What needs to change? Is it more autonomy, less autonomy? How do we fix this for the unique requirements of flying a UAS? It is different. I'm a pilot, I'm both. And I'd love to be able to say it was the same, but it's different. And what they've also found is young pilots who have grown up with joysticks and flying their computer games and working their computer games at home prefer the computer control type situation versus somebody like me who's come from a manned platform who prefers stick and rudder type controls. And either we haven't demonstrated one as a preference over another just based on your previous expertise. Over time, that probably will change, but right now there's no preference. So what we have currently going on, I mentioned a little bit, is the secure command and control link and interference. A lot of concern about maintaining that link, the sanctity of that link, the control of that link, and then if you lose it, how to get it back quickly. That group is forming the Industry Standards Board 228, Working Group 2, on what those procedures will be. The FAA will just sign on to what these new industry standards will be. A lot of what we're doing now is not going right directly to the FAA for regulations. We're informing industry standards groups, consensus groups, to our recommendations of what the industry standard should be, the minimum standard should be. If you move on, again, we have some follow-on work in the collision studies I'll cover. We do a lot of work in STEM. These kids today just love, you fly a UAS around, you can teach them math out of that, you can teach them physics, you can teach them, and they won't even know they're learning programming skills. So we've gotten involved in some of that, and we're looking to expand that out. A couple other issues that have popped up in some discussions is detecting and avoiding counter UAS. Under our FAA mandate, the FAA has no authority to bring down a UAS, none. Matter of fact, Title 18 forbids really anyone from bringing down a UAS. There is some waivers that have been put in place for Secret Service and Department of Homeland Security in certain situations in the FBI, but that can't happen right now. So we're trying to develop what that needs to be, how to detect it, how we re-vector aircraft, and then in some of the work that we got coming on from DHS will be, okay, so now what do we do when it does come time to take it down? What legislative rules do we need to put in place to make changes to allow that to happen? E-commerce. So as you start using UAS in your day-to-day roles, take it refinery, a power line inspection, or package delivery, leaving from some warehouse to deliver things to either different work sites or to home delivery, it's going to change the air traffic system. We're going to have these other vehicles flying around, and we're now looking and trying to forecast what that will look like so the FAA can prepare itself and make adjustments to its air traffic system so it can handle the increased capabilities in that area. Okay, so we'll take a deep dive. This is the air-to-ground study. This is the good news story. And as I go through it, you'll go, oh my gosh, maybe I really hate to hear the bad news story. But what we did with the air-to-ground study is we looked at what happens when a UAS hits somebody, people or property on the ground, houses, car windows, you know, when they crash into a car driving down the highway. What would be the effect of that? The overall good news is the FAA was regulating to a level that was used on the national test ranges in commercial space. So it's things like missile systems, space systems, which tend to be metallic, hard metals, titaniums, those kind of things. And you look at the standard UAS today, they're mainly plastics, right? So there's some big differences here. So when they initially looked at the problem of UAS, I just threw this up here briefly, you had to break down that into a taxonomy that they could work with. So it's kinetic energy, sources of ignition, and rotating components. So think propellers, the fuel, or in most cases for smalls, it's the batteries. We'll get back to battery issues, battery issues, battery issues. They're not just on the skateboards. We have some problems with those in the air also. And kinetic energy, the speed and velocity and what that does to people. So what you're going to see here on this slide is on the left-hand side, there's our dummy. A dummy will pop up here on the right. As the drone falls, what I want you to watch on the left-hand side is how that drone, when it hits the crash test dummy, how it flexes and rolls and flips and does all that, and compare it to a wood block of the same weight that will come down and hit the dummy. What you'll notice on that one is it stays on the dummy's head. All that energy is transferred into the dummy. Eventually, it is retracted to protect all the equipment on the ground. You'll see it eventually leave, but that's a retraction wire that pulls it back up. There is no wire attached to the drone. So on the right, all that energy went in right into the skull, and you can just see all that flexing and how far off the head that UAS leaps. That's all retained energy. That was not transferred to the head. Again, just one more time. And that's going to be useful in my next slide to show you what the impact of that is compared to what the FAA was doing. Okay, so if you just look at the very bottom here, it says Range Commanders Council Standards. And let's focus on the right two columns closest to me, and the probability of head injury or head impact. On the bottom, it says probability of fatality from a head impact, a chest impact. And you'll see almost 100% that you're going to die from a 2.7 equivalent DJI Phantom using the FAA standards. That's what they thought was going to happen. If you look at when we took a piece of wood and a piece of steel that they used to do the work of the Range Commanders Council, we correlated those results with the probability of head injury at 99 to 100. Okay, so if it's steel or wood like you planned, it will likely kill you if it hits you in the head at the speeds we were dropping these things. Now, you go to that far left column, you can see down there the chance of fatality was 98 to 99% is what they were figuring for that UAV at 2.69, and the speed that it fell a little bit slower at 49 to 50 feet per second was about still close to 100%. But if you go up to the probability of a head injury, it's 0.01% to 0.03%. The FAA did not like seeing this. This could not be true. The dummies were not reacting like a real person would react. So they had us retest this and prove this all types of different ways. We're even doing more I'll get to here in a second to prove to them that it's the flexibility in these drones that were actually allowing almost an order of magnitude difference in what would hurt you. So what the FAA thought would kill you at 2 pounds really wouldn't kill you till it was about 20 pounds. Okay, they're likely to kill you. So they were over conservative and restrictive in what you could do with your UAS. So the findings of this report, they went through all kinds of methods and means to try to figure out, okay, what do we need to regulate? Everything from toy standards to car crash standards. And what they found basically were 3 basic injury methodologies that cause problems. What's going to kill you is blunt force trauma, that impact, mass, and velocity hitting you in the head, neck, or thoracic region. So that's where our focus was. But we also know, and we saw, a lot of lacerations, both in the modeling community. Toy industry's already set up a lot of standards in this area. So what we told the FAA for operations over people, our recommendation is that you have blade guards on. And the industry is already adjusting based on our report. What looks worse is that little kid who gets a cut and is all bloody, and really there's no risk to life, but it looks horrible, right? So we want to get that squared away. Canada was regulating on kind of puncture. What was the likelihood that you'd get punctured and stabbed? Well, that depended so much on the way, the axis, and where exactly that UAS hits you. What we recommended was we don't use that metric. Blunt force trauma will work, and that's where we focused. A couple things they found. The FAA believed these things would fall ballistically, that the same speed as a rock, that UAS would come down. Well, the coefficient of drag on these things caused them, even when they're going full speed, less than 10 feet above a person, you would think, at 30 miles an hour, when it fell, in that 10 feet, it was over a 45-degree impact. So you would be getting more steep impacts on the head, and the likelihood of getting that side hit was very, very limited. They also saw that you saw that UAS flexing, but the cameras don't, and the motors don't, and those hard parts are something we're going to have to look at more in the future. So what the follow-on is happening, this has been approved. We're working more studies. We're doing different UAS to validate that it wasn't just this DJI Phantom and fixed wing that we used. We're validating it on models, test dummies, and I'm looking for human volunteers. They said I'd find a few here today that we could actually throw some of that. Actually, we're doing some cadaver matching to validate the deaths, because again, there's a couple of people in the FAA who've been doing this forever who just do not believe it's true, and they think that crash test dummies are lying. So we found some cadavers that can talk back to us through sensors, and they'll let us know if it's true. And then based on that, the goal is to develop a very simplified test so that anybody who builds one of these UAS will be able to define that flexibility, and they can put a risk number on it, and that'll allow you operations over people in accordance with the safety ConOps that you develop. So that's a good news story that we can go to. On the air-to-air study, didn't surprise me any, but this is a bad news story. Anytime we have two aircraft hit each other in the air, it's not going to be good. This wasn't a risk study. I have to hammer that down. Risk also looks at the probability of impact. What we actually did is we took the absolute worst case scenarios, center of mass against center of mass, to see what would happen when we hit an airplane. 737 A320 class aircraft and a business jet, Learjet 31. And the UAS, the projectiles were the Phantom 3 and a Precision Hawk Lancaster. It's a bit of an eye chart, just green to red. Green is not so bad, red is really bad, is pretty bad. The green is like a little dent. Yellow is a deeper dent into a structure. Yellow, that amber yellow, darker yellow, is there's a puncture, you actually puncture the skin somewhat. And red is you damage interior to the aircraft. The battery study, I'll just discuss that now. What they found with the lithium polymer batteries is when it hits at high speed, even if it were to parts go inside of the aircraft's wing structure, for example, it is so destroyed that there's no fire. Or if it doesn't penetrate at all, it just shatters and goes off, there's no possibility of fire. But in some slow speed modeling, when the battery wedged itself in there was an increased risk. We don't know, we haven't been able to define that risk yet. We're looking to do more battery studies in the future of a potential fire. So for the airliner, you can see some pictures here of the two airliners in different, got the quadcopter on the left, which is a little smaller than the fixed wing. In all cases, the fixed wing is worse, and I'll explain some of that, why that is. And the quadcopter is less so. You can see the damage on the aircraft is going to be less for the commercial airliner because higher required standards of carrying all those passengers versus a biz jet. And then the same thing down here. Here's the Learjet. And on the previous slide, there was cockpits were only yellow. You're going to see here with the fixed wing aircraft, we now have a situation where we had penetration of the canopy, which was a major concern to the FAA. Now the pilots are at risk. Quadcopter less bad than the fixed wing. So as you look at these hits on the left, we were asked to compare it to a bird strike. That red blob is basically a model of a bird. The middle structure is a quadcopter, and the far right is a fixed wing. And in each case, as you move across, the damage caused by the bird is less than what's caused by the quadcopter, which is less than caused by the fixed wing aircraft. So in comparison to bird strikes, UAS are worse than bird strikes. So the standards out there that the FAA applies to birds need to be adjusted for UAS because they're stiffer. Oops, moved ahead here. Because they're stiffer and they alignment. We're going to talk about that here. As a UAS picks up speed, all my engineers in the room know this, energy equals mass times velocity squared. So as the mass increases, we get more structural damage. As velocity increases, it exponentially increases the damage to the aircraft. So high-speed impacts are bad. The slower the aircraft is, obviously, the better. Stiffness of components. So those batteries, those motors really cause the biggest problem. It's not the plastics on the UAS and how they're aligned. So think a quadcopter where you have motors kind of all the way around the aircraft, and then your camera's in the middle somewhere. When that hits, it is not as bad as that Lancaster who has a propeller with a motor all aligned with the battery and aligned with the camera, which will go well into a lot of these structures a lot deeper. Moving on. We also looked at engines. We took an engine that the FAA model. It doesn't represent really any engine out there. We just did it for a quick look to find out if we're going to do more engine studies. And what we found was the same thing. The fixed wing is worse than the quadcopter. The further out on the fan blade you hit, the worse the situation. And the higher the speed of the fan blade, so a takeoff scenario, causes the most damage. We are working with the engine manufacturers right now they're recommending that they all collaborate and develop an engine for us, none of their own, but using capabilities of all their different engines to do the next study. So we're on path to do this, and the bottom line is we do not want airplanes to hit. So a big key here is the detect and avoid. We've got to keep aircraft apart. If they find each other in airspace, we're going to have bad things happen. We're looking at rotorcraft and GA aircraft because they're down in this environment where a lot of these smaller UASs are. One thing that came out in the study was, well, you did all worst case. Is the boundary layer going to have any effect? As air flows over a wing or around a wing or over the cockpit, will it have an effect? We did not look at that in the first study, but the follow-on work, we're doing a quick look at that and see if it decreases the probability of that direct hit and reduces the level of damage. And then we're working on the engines. The engines, it's never good, even when a bird goes down an engine, it'll trash an engine. But you got to be able to shut down the engine. It can't vibrate. It can't fall off the wing. We'll be looking at all that with the engine manufacturers, and then with the hopes to design UAS in the future to mitigate damage to engines. And with that, I'll leave questions to the panel discussion, but that's kind of where we stand today. And I would say just keep those, the seriousness of some of these things. They're not toys, even though a lot of our kids are running around with them like toys. They are aircraft, and when they're in the national airspace, they can cause quite a bit of damage. Thank you.